so please ask a lot of questions. So this is work trying to explain something about the performance of deep versus shallow neural networks for function approximation. It's joint work with Xiu Liang, who's here. So the outline of the talk is I'm going to, although most of you must have heard of neural networks, and it's very popular. In fact, when I tried to recruit Xiu, he said he'll work with me only if I work on machine learning. So I had to come up with a new problem. So I'll talk about what a neural network is, and I'll talk about some prior work and our main results. So let's talk about what a neural network is. So a neuron is just essentially a nonlinear function. So you take a scalar x as input, and then it produces a output sigma x. So there's some very popular nonlinear functions that are used as neurons are a threshold unit. A threshold unit simply outputs a +1 if the input is positive, -1 if the input is negative. The second one, I think it should be a rectifier linear unit. It's a dumb name for something. Basically, it's x plus. So you give x as input. If it is positive, it passes x. Otherwise, it gives a 0. Some electronics geek must have named it. I guess must be like the diode response function. I'm not sure why it's called a rectifier linear unit. And a logistic unit is essentially a continuous approximation to a threshold unit. Okay, so these are some popular neurons, and there are also other neurons that are used. The simplest form of a neural network is just instead of giving a scalar input, let's say you give it a vector input. Let's say the components of the vector are x1 through xn. The output is just simply w transpose x. So sigma of w transpose x. Okay, so w's are called the weights. And one minor point which might be useful to note is if you set one of the xi's to be a constant, then it adds a bias to it. So it shifts instead of, for example, if you're using a threshold unit, instead of it giving you a +1 when the input is greater than 0, it might give you an output of 1 if it is greater than half, for example. So you can shift it by making one of the if you instead of thinking of the input vector as just a variable, so you think of n-1 of those input dimensions as the variable, and then 1 is just held to be a constant. So just shift what you're doing. So you can add bias to the neuron. Okay, so this is how a neuron is used, and the neural network is essentially composed of multiple neurons. So you give it an m-dimensional input. You pass these inputs possibly through neurons, and then take linear combinations of them, pass it through more neurons, take linear combinations, pass it through more neurons, and so on. Okay, is this clear? So in this example, there are m neurons in each layer, and there are L layers, and finally there is an output that's just one-dimensional. Okay, is this clear what a neural network is? I'm assuming most people have seen it, but just in case, just to be clear. And when I say a deep neural network, or when anybody says a deep neural network, it's a network with many layers as opposed to 1 or 2 layers.
But deep learning is shallow. Is that true?
Deep learning is a shallow field? No, it's not. Could be a shallow field too. I thought that's what you meant. So what is not the focus of the talk is what is done in practice, which so I'm not going to say anything useful practically, so this is a purely theoretical talk. So the way a neural network is really used is that you give it a lot of input. I mean, it's a supervised learning environment. So for example, you might give the vector could be a vector representing the pixels of an image, and maybe you want to distinguish between a panda and a baboon, and then you give it lots of examples of pandas and say that you should output a +1 now, and you give it lots of examples of baboons, and you say you want to give it an output of -1. And most of the practical work on neural network is how to choose the weights so that the neural network correctly gives the output. Okay. This is something I'm going to completely ignore in this talk. That's probably the more useful part of the of research in this area. But to some extent, that is also the more shallow part, in my opinion, from a research perspective. So here I'm going. So what people have observed is that deep networks perform better than shallow networks, meaning that if you add more layers, the network performs better, and in a sense that I won't get into. But what I am going to talk about is to try to understand why this might be the case from a function approximation perspective. Okay, so I'll talk about what the function approximation problem is, and I'll talk about it. So I'll talk about it from that perspective. And for the purposes of this talk, I'm going to assume there are only two types of functions that are allowed, the two types of neurons that are allowed. So you give it the neuron an input, it produces the sign of the input as the output, or the rectifier linear unit, which just produces plus. These are the two most popular neurons anyway. So let me talk about prior work. The prior work in this area, so many people have studied the following problem. You can think of a neural network as taking an input x and producing some output f tilde. Okay, and the goal. So then you say that I'm interested in approximating functions in a certain class. So typically the function class is considered to be a set of continuous functions. And the question you ask is that given the set of continuous functions, class of continuous functions, and a desired accuracy epsilon, can I always find a neural network? Meaning find a network with a certain number of layers, certain number of neurons in each layer, and a certain value for the weights that approximates the function with an accuracy of epsilon. Okay, so this is the classic function approximation problem. The very first problem of this type was, of course, the very famous result by Kolmogorov and Arnold called the Kolmogorov-Arnold representation theorem, which was done in response to Hilbert's 13th conjecture, where they proved that the conjecture was false. I don't know the original version of the conjecture, but the basic problem Hilbert posed equivalently, apparently, which is equivalent to the 13th conjecture, is that can you represent, the question he asked was, can you represent a d-dimensional, a multivariate function which takes a d-dimensional input and exactly recreate it using univariate functions, using compositions and additions of univariate functions. And it was, I don't completely understand the history because different places seem to suggest slightly different things about this. I think the version that I seem to believe is that Kolmogorov proved that you can use it, you can do it using, take any high dimensional function, you can approximate it using compositions and sums of two functions with two inputs. And Arnold, who was his 19-year-old student at that time, he basically said that he can actually do it with just univariate functions. So it's a famous result called the Kolmogorov-Arnold representation theorem. But the main difference between what we do in neural networks today and the Kolmogorov-Arnold representation theorem is that they were actually exactly, so it's a pointwise result. We want to take a function exactly represented using univariate functions. Whereas in neural networks, people relax it and say, I'm interested in an epsilon approximation in some norm. Often the norm used is either the infinity norm or the one norm. In my talk, I'm going to use the infinity norm, or much of the earlier work uses one norms. And this was done by George Sybenko, Hornick, and Andrew Barron. And Sybenko and Barron were actually professors in ECE at Illinois when I was a grad student. They did this work when I was a grad student, actually. And I took the information theory with Andrew Barron. Yeah, that's cool. Yeah, so the difference between the Kolmogorov-Arnold result and the results of Sybenko, Hornick, and Barron is that because Kolmogorov and Arnold was trying to exactly mimic a function, the univariate functions that have to be used to approximate the high dimensional function turn out to be very, very complicated fractal type functions. So you can't really use them in the learning context, whereas the neurons that are used in today's neural networks are very simple, of the form that I showed in a couple of slides ago. Okay. So if you look at these earlier results, you can see that you can achieve function approximation. You can get a degree of error epsilon by either increasing the number of layers or increasing the number of neurons per layer. And the question is, which one is better? Okay? And my answer is going to be the deeper networks, meaning more layers are better. And there is work related to this as well. So much of the earlier work on this topic, basically they say that I'm going to give you a network with 3 layers. Okay? A particular network, so I can construct a particular network with 3 layers. If you try to approximate it with a 2-layer network, if you try to mimic the function of the 3-layer network with a 2-layer network, then the number of neurons that you need becomes exponentially larger. Okay? But that's for specific examples of The result there is I can give you a 3-layer network that if you try to reduce the number of layers, the number of neurons increases. What I am going to try to do is that I'm going to show you that there's a large class of functions such that for every function in this class, using a deep network always gives you much smaller number of neurons than a shallow network. And the reason for trying to use smaller number of neurons is that means also that you have smaller number of parameters in the system, and so you'll have less problems with overfitting and so on, although I haven't tried to connect this to VC dimension or things like that yet. At this point, we're just simply saying that we need a smaller number of neurons. Okay, so the main results, most of the results, I'm going to take the simplest case and hopefully illustrate it using pictures or very simple concepts. I'll break it down into 2 parts, achievability and lower bounds. Yeah, there's a question there, yeah. Yes, it's a feed-forward neural network. There are many variants of neural networks. There are recurrent neural networks. So it's just only for feed-forward neural. The architecture that I've described is what's called a feed-forward neural network. If you want to track a dynamical, so this just simply a feed-forward neural networks are used to approximate a function. If you want to approximate a dynamical system, then you need to have feedback loops in there, and that is what is used for self-driving cars and things like that. I'm not talking about this here. Yeah.
Can you also say something using approximation was it some sort of constraint in the neural network? So if I was here approximating, say, functions with polynomials,
right.
Some class of basic.
Right, that's what I'm going to say, what type of functions I'm going to approximate. Is that your question, what type of functions?
My question was trying to make a distinction where you're trying to constrain the problem where you're doing these approximations with univariate functions.
Mm-hmm.
That's something to do with the fact that you have these neural networks, as opposed to general polynomial basis functions.
Yeah, I'm not talking about that here. So the motivation here is that the type of neural networks that I talked about, where you have univariate functions and you're doing linear combinations followed by compositions. Essentially what it is a composition of linear combinations of compositions of linear combinations of compositions. I'm taking that architecture because this is widely, practically it's been shown to be easily trainable. Okay, that's the motivation. Now one can ask this question much more generally, and I have not even thought about it, so I don't know what to say about it. Okay. So this is the main achievability result. So the result says that for sufficiently smooth functions, which means that actually it can be piecewise smooth as well, which means that it has to be sufficiently differentiable. You can construct a neural network with order log 1 over epsilon layers, which uses order log square 1 over epsilon neurons, and achieve a function approximation of epsilon. So to achieve a function approximation of epsilon, we need log square 1 over epsilon neurons, and this network will have log 1 over epsilon layers. So this is the main result, and I will primarily. This might seem a little silly, but I think most of the ideas can be expressed by taking a scalar input actually. So I'll tell you why that is, and then the extensions to multivariate functions will be discussed later. Okay, so I'm going to take a sufficiently smooth function on R, okay, and approximate it using a neural network, and then the result extends to multivariate cases. The basic idea is actually just understanding how to approximate a univariate function using a neural network. The converse to this result is how good is this result? I mean, can you do better than log square 1 over epsilon neurons? Okay. To do that, we have a converse result which says that if I start with strongly convex functions, okay, the class of strongly convex functions, then there is a relationship between the number of layers and the number of neurons per layer that must be satisfied, which is to get a function approximation of epsilon. So you need to, m raised to the power of L has to be of the order of 1 over square root of epsilon. Okay, so this is why this proves that the upper bound is tight, I'll get in a second. But I just want to mention that we saw a result like this in a paper by Dasgupta and Schnitger in 1993, who present a result like this in a machine learning conference without any proof. So it's quite possible that they knew this something like this. So I emailed the first author, who turns out to be a professor in computer science at University of Illinois Chicago now. I don't know where he was at that time. And he sent me 2 technical reports saying this contains all the proofs. And then the proof of the one theorem that I need is not in either of the technical reports. I emailed him back, and I haven't heard anything yet. So, but I have a feeling that they must have. They had the result for x squared without a proof, and it's possible they could have extended it to strongly convex functions, and x squared are not that different. But I'm going to present our version of the proof. I don't know what they had in mind when they got this result. So why does this result provide a lower bound on the number of neurons? Now I told you that m raised to the power of L, I'll prove later on that it has to be of the order of 1 over square root of epsilon. So given that that's a fundamental bound, then you can minimize the total number of neurons, which is m times L, because m is the number of neurons per layer, L is the number of layers. So you want to minimize ml subject to the constraint m raised to the power of L is greater than or equal to 1 over square root of epsilon. And then that shows that the number of neurons it requires is log of 1 over epsilon, and our result is log square. So which is it's within a log factor of the optimal solution. And interestingly, if you use a fixed number of layers, for example, if you use one hidden layer in the neural network, then the number of neurons you need is 1 over square root of epsilon. So our result says that you can do it using order log square 1 over epsilon, using a deep network, meaning the number of layers has to be of the order of log of 1 over epsilon. As if you use a fixed number of layers, which is what I call a shallow network, then you get 1 over square root of epsilon. So this is a spectacular reduction in the number of neurons required by using deep networks. So this is the main result. Is there any questions on this? So the rest of the talk is about hopefully conveying the proof. That's interesting. So it's not totally obvious. So I'll show you one. So as you do more and more compositions of linear pieces, you're basically getting a piecewise approximation which has m raised to the power of linear pieces, which means that as L becomes large, you get lots of linear pieces. But on the other hand, the number of parameters you have is only m times L. So those m raised to the power of L cannot be, it's not arbitrary. Yeah, so in one sense it does appear intuitive, but so you can't control all the m raised to the power of L pieces. That's the difficulty. Yeah.
Because intuition part, you wonder whether if I allowed you more than one function, because you're only building it based on.
Yeah, so here I'm going to assume I'm allowed 2 functions, but you can reduce it to 1 function, you're right. But for simplicity, for the sake of proof, I'm just going to use 2 types of functions. But the intuition is partially correct, but it's not. So you get m raised to the power of L linear pieces, but there are only m times L parameters in the system. So you can't really control how the slope and the intercept of each linear piece separately. So there's something funny about that. Yeah. Okay, so the rest of the talk is about providing the intuition. Yeah.
Question. I still, on the first layer, you matched each of the 2 neurons. What's the benefit of adding more neurons and inputs? How do you do that mapping in the first?
So I will tell you what the entire construction is in a second. Okay. So yeah. Well. Okay. So if you think of the first layer, maybe the first layer gives you a set of hyperplanes. Okay, so it takes a real valued input and then says whether the real valued input is on one side of a hyperplane or another side of a hyperplane, right? Now you take linear combinations of this. So now you have taken a real valued input and converted it to a binary vector, and then you're looking at hyperplanes in that space of binary vectors. So it is very easy to come up with examples just with one layer where you cannot come up with an answer. Or you can, but I think it's much easier to do it in multiple layers. But in this construction, you'll see why I need multiple layers. Okay, so I'm going to try to prove this result. So first, let's think about approximating the simplest function fx equal to x. This is a trivial problem. So I went through this maybe a little too quickly. I'm assuming x, the input is between 0 and 1. Okay. since the input is between 0 and 1, x plus is the same as x. The positive part of x is the same as x. So all I need is just a single neuron. So I give it an input of a single I give it x, and then sigma of x will give me the x again. It's a trivial. But I'm going to do it in a more complicated fashion. I'm going to approximate x in a more complicated fashion, which will actually be useful when we do x squared, x cubed, and any continuous function later on, and any smooth function later on. Okay? Sorry?
We're impressed.
So a useful way to think about this problem is that suppose I'm given a number between 0 and 1, and I want to do a k-bit binary approximation. I want to represent it by a k-bit binary number, okay? And that, of course, a k-bit binary expansion of a number between 0 and 1 gives you a 1 over 2 power k approximation. This is where the log 1 over epsilon comes. So k-bit binary expansion gives a 1 over 2 power k approximation. Reversing it, if you call 1 over 2 power k epsilon, then to get an epsilon approximation, then I need log 1 over epsilon bits. And I'm going to show you that I can extract the first k bits of a number using a neural network. Okay? And this is one of the principal ideas, and then there's only one more idea, and that's it. That's the entire proof.
Mod 2 map, right?
Huh?
Equation of a mod 2 map would do that.
Mod 2 map. I want to represent it using neurons here, so that's the specific types of neurons.
You multiply a number by 2 and mod it with 1.
Yeah, it's essentially that. Yeah. So it's basically that's the same thing as asking whether the number is, yeah, so that's exactly that. Yeah, and you have to, so if you recognize that can be represented using the type of neurons that I said, then you're done. But then it's the second stage, and then I have to somehow use this to represent other smooth functions. Okay? So I think what you are saying is essentially, another way of saying is that what is the first bit of a number between 0 and 1? It just tells you whether the number is greater than or equal to half and less than or equal to half. The second bit is just telling you whether the number minus the first bit divided by 2 is greater than or equal to 1/4 or less than or equal to 1/4. Each of these is just a threshold operation, right? You're just passing it through a threshold, and then you're just subtracting something. So it's just a linear operation and threshold operation. Linear operation, threshold operation. So this can be, what happened here? Oh, I guess there was yeah. So extracting the bits of a number between 0 and 1 can be done by a neural network. Now here's the important trick. So now suppose I want to approximate x squared. Okay? I can approximate x squared by looking at the binary expansion of x and multiplying it by itself. Okay? So that can be represented like this. So this is, do you have a pointer by any chance, Sean?
Yeah, I do.
Okay.
There, and it's on.
Okay, thanks. Yeah. So this is just the square of the binary expansion of x. So that can be written as xi times 2 power I multiplied by this. So it's basically, if you look at each of these terms, there is a weight 2 power minus I, and you're multiplying a bit by a real number. Okay? So the only thing I have to show you is that a bit multiplied by a real number can also be represented by a neuron. And this is, Shiu made this really nice observation. X times r is the same as max. So if x is a bit and r is a real number, then x times r is just nothing but maximum of 0, 2 times x minus I plus r. This is obvious because if x is 0, the left-hand side is 0. This is minus 2 plus r. R is between 0 and 1, so therefore this will be negative and this will give you 0. Whereas if x is 1, then this becomes 0 and just gives you r. This is it. And we know this is just a linear combination of x, r, and minus 1 passed through a ReLU. Okay, this is it. Okay, this is the entire talk. And then of course you have to write theorems and stuff like that to make it more complicated. But this is the this is the basic idea. Okay. So to summarize, to approximate x squared, we first extract the bits of x, multiply them together. That can be represented as a multiplication of a bit by a real number. And the key property is that each of these steps can be represented as a linear combination and using a threshold unit or rectifier linear unit. I mean, if you want to show it, if I want to see it pictorially, it is like this. I'll skip that. Okay. Extend the same idea to x power p, extract the bits, raise it to the power of p. Each of these, you'll have lots of terms involving x times r, and then you can go through the same argument and show that. So now there will be a dependence on the order of the polynomial, okay, which I did not show originally. And the main thing is the main slightly mathematical part is to how to approximate piecewise smooth functions. So basically we know smooth functions, I mean continuous functions can be approximated by polynomials, but the problem is that to control the degree of error, and what you do is that you do a polynomial interpretation at specific points called the Chebyshev points, and if you do that, then you can bound the error very precisely so that it still maintains this log 1 over epsilon form. Okay, so you can look at the paper. The paper is available on arXiv. And we've also submitted, this is unusual conference where it's a conference where you submit the paper, they publicly put it up, and anybody in the world can comment on it. This is the way it is. It's an open review process. So you can be either publicly shamed. It's apparently the main neural networking conference, so we thought we'll try it. We'll see what happens. And somebody told me ours is the only paper with no simulations in the entire list of submissions, so I don't know good or bad. So you can also, so this is closer to the traditional work on function approximation. You can extend the result to higher dimensions, and we are not able to extend the result to arbitrary functions in higher dimensions. We are able to extend the results to smooth functions composed with polynomials, which actually is a large, almost every function that's been studied, for example, in Barron's work or other works are of this form. So for example, e raised to the power of w transpose x would fall in this class. Okay, and there is a dependence on the number of dimensions in this particular manner. Okay, so all of this is pretty straightforward.
Is that what you expected?
At least this is consistent with the Barron's work. So I don't know. So unfortunately, we don't have a lower bound which captures d. This is something that I don't know whether you need the dependence on d or not, but it's at least consistent with prior work. The lower bound we are only able to show in terms of epsilon, not in terms of d. That's a good open problem. I don't know. This is some intuition as to why it works in higher dimensions, but I think it's not that difficult. I'll skip this. Okay, so now the lower bound. So the lower bound, I said, was the lower bound basically follows from this fact that if m is the number of neurons per layer, L is the number of layers, then m power L has to satisfy a fundamental bound, which says that if you want an epsilon approximation, then m raised to the power of L should be greater than or equal to 1 over square root of epsilon. Okay? Why is this? The basic idea is that if you look at neurons of these two types at least, then essentially all they're piecewise, they're linear approximators. Okay? And it is not very difficult to show that if you have a function like a strongly convex function, to get an approximation error of epsilon, we need at least 1 over something like square root of epsilon linear pieces. And why is this? It's pretty easy to see this. So suppose you look at the function in the interval 0 to 4 square root of epsilon. You can draw a straight line trying to approximate this function. You can move it up and down however you want, and then the amount of error will be 5 epsilon. There's nothing you can do about it. Okay? To make it less than epsilon, it automatically means that you need at least one more piece in this. Okay? So and then you recursively do this argument, split the interval between 0 and 1 into tiny pieces, and show that in each of those pieces you need at least two straight lines, and then that gives the answer. Okay? I don't know why I repeated this. So then the question boils down to, so I just argued that to get an approximation error of epsilon, you need 1 over square root of epsilon linear pieces. So how many neurons and how many layers and how many neurons per layer do you need to get the 1 over square root of epsilon linear pieces? So if I answer this question, then we are done. And that is actually pretty straightforward, and I have a feeling that Dasgupta and Schnittger must have known this. So if you take two functions, the first function has m1 breakpoints and the second function has m2 breakpoints. If you add the two up, sorry. You can get a function with at most m1 plus m2 breakpoints, right? You can't have any more breakpoints than that. And then let's say you pass it through a rectifier linear unit. A rectifier linear unit outputs, for example, a biased rectifier linear unit would output the function when it is above 1 and output 0 when it is below 1. If you do this, then at most the number of breakpoints can become 2 times m1 plus m2. So if you start with two functions, one has m1 breakpoints, another one has m2 breakpoints, the only type of operations we are allowed are linear combinations and passing it through neurons. And so after one step, all you can do is have 2 times m1 plus m2 breakpoints. So which means if you start with m functions each with k breakpoints, if you pass it through a many-layered neural network, it's very easy to show that you get m raised to the power of l breakpoints. Actually, the earliest result of this type that we have seen is by my colleague in computer science, Matt Stelgarsky from 2015, although I don't know this. Dasgupta and Schnitger might have known this result. Okay? So which means that 2m raised to the power of l must be at least greater than or equal to order of 1 over square root of epsilon. Now this gives the upper bound. So now if you fix an L and you get a lower bound on the number of neurons, or you can optimize ML to get a universal lower bound on the total number of neurons required. Okay? And this shows that if you use a fixed number of layers, meaning number of layers is independent of epsilon, then you'll need a huge number of neurons. And secondly, if you use it optimally, then our result is within a log factor of optimal. Okay? I think that's the conclusion. So I went a little faster just to get us back on time for lunch. So for approximation of functions with enough smoothness, a shallow network requires substantially more neurons than deep networks to achieve the same level of accuracy. And the main quantitative results are that you need log square, not you need. We have a construction that uses log square 1 over epsilon neurons, whereas the lower bound for any network is log of 1 over epsilon. And if you use just a single hidden layer or a fixed number of hidden layers, it will be polynomial of 1 over epsilon. So in that sense, we get a near exponential reduction in the number of neurons by using more layers. That's the main point. Okay? Thank you.
Questions? Must be, yes.
Oh.
When you have when you go back to the 0 point, the binary expansion.
Oh, the binary expansion? Yeah.
Yeah. So.
Yeah, so she's an information theorist. That's what she focuses on, okay?
So that's exactly like the Huffman code, right?
It is, but it's basically just a very simple idea. So all it is, yeah,
No, I'm wondering, so have people looked at this for doing computation on?
Well, Huffman code, I think of it as you have a distribution, or you have a bunch of letters in an alphabet, and you're trying to minimize the number of bits that you're. Yeah. So here, all I have is a number between 0 and 1.
Right, but the construction and the interpretation is the same. So have people looked at this, for instance, for computing or approximate computing on compressed data? You know, because that's one of the big.
I don't know. I don't know the connection actually. I haven't looked. I haven't thought about.
Basically, it's like you were multiplying 2 Huffman coded.
I see. So I think that here the main point is that everything that all the operations that I knew that I can do are constrained to be of a particular type. It has to be approximated, but not necessarily exactly done by a neuron.
But they're all, I mean, as you were saying, they're basically all, binary plus, plus an offset. So I was just wondering, have people looked at doing things like this for, have you applied this to computing polynomials on
compressed data? It's possible. I don't know. So basically, the question you're asking is that can you take a neural network to do a computation of this form?
On the compressed data.
That's possible. I don't know. Yeah, I don't know. At least I haven't seen it in the function approximation literature that any connection made between this and.
There isn't that much of computing on compressed data.
Okay.
Very, very little. So
Okay.
that's what
I see. I don't know. I'm not aware of it. Yeah. Thanks. That's a good comment, though. Yeah. Yeah.
Is there anything that's known about, suppose that the function has a singularity in it somewhere, and what happens to neural networks?
By singularity, if it's just a jump, are you talking about something
Queuing context, will you bring over into 1 over 1 minus rho?
oh, like that, it's going after infinity, yeah. I don't know. I think the only things I know are continuous functions, and then you can extend it to piecewise continuous functions. But I don't know what if something escapes after infinity. I'm not sure what happens in that context. I know people. I talked to Balaji Prabhakar somewhat recently, and he said he is trying to use neural networks to understand traffic in data centers. So I don't know if he means that he's looking at the queue behavior or just simply the arrival rates. I don't know what he's even trying to learn. So he might be somebody to, he said Google is interested in this, and he said he's been working with them with some students on this topic. It would be interesting to find out what he's doing with it. Yeah.
So do you have the assumption, so we have known that shell level without limit can approximate a universal function.
Mm-hmm. I mean, if a shallow network can do it, a deep network can also do it because you can set the weights to be 0. Yeah. So I guess the previous, sorry, go ahead.
In case you limited the function into smooth function, right? It's not really
The functions that I'm considering are piecewise smooth. Yeah. So not arbitrary continuous functions. It has to be differentiable. It has to have derivatives of a certain order. Okay, that I did not specify here. Yeah.
And here you choose the number of neurons, the number of total neurons. Depends on the approximation error.
Mm-hmm.
My question is for considering the continuous function, will the total number of neurons will also depend on the bound of the, for example, first or second order derivative of the functions that we need to approximate. I mean, whether this kind of the total number of neurons will also be a function of some kind of bound of.
I don't. I'm not so sure because those. At least if you think of polynomials, for example, any x bar p is going to be between 0 and 1. So the only thing that matters is the coefficient in front, and that will probably appear as a weight in the neural network rather than any other approximation error.
Because not just thinking about to approximate the topological center, which is a function, just kind of goes down and then very kind of.
Sharp drops. Yeah. Of course. I think if you have an arbitrary continuous function, you have to somehow do a polynomial interpolation. There, the error might depend on how sharply the error must. So the Chebyshev point approximation. I don't know how the derivatives enter in the approximation error.
Yeah, actually we assume the derivatives of the higher orders is bounded by.
Yeah. Okay, so otherwise that constant might appear. Okay.
Yeah, so
Okay. Yeah, so I think you're right. So it will if it becomes arbitrarily steep, that'll probably show up somewhere in the constants. Yes, you're right. Yeah. Or an approximation to the real.
So right now we are presenting all these things. A is truncated as
Mm-hmm.
So if we right now we are presenting x1 to xk all at once,
Mm-hmm.
getting one output.
Mm-hmm.
So if we were to treat it as a sequence and sort of use a recurrent network,
Mm-hmm.
would this sort of lower the?
I have no idea. It's a good question. Yeah, I haven't thought about any networks with feedback in it. Yeah, so I don't know what happens with feedback. Yeah, I see what you're saying, but I don't know how to do that even for polynomials. I'm not sure how to do it. Yeah.
Okay, great. So time for lunch, and thank you once again.
Thank you.
Beautiful.
Thanks.
Miss Illinois. So lunch is at the right union, which is here, around the corner. There's a food court. Toyota Traffic. And that's the thing, I think we can leave our variables here. I'm going to walk it up. So let me confirm.